Okay, so we can go ahead and use the second derivative test. So again, we're asked to find the local extrema of a function. So we'll go about this the same way. The first thing that we do is take the derivative. So we'll get 15x to the fourth minus 15x squared plus 0. And then we can factor this, so we can pull out a 15x squared from both terms, and we'll get x squared minus 1. So setting each of these pieces equal to 0, we'll get x equals 0 as one solution, and we'll get this, so x squared equals 1, which means x equals plus or minus 1. Okay, so our critical numbers are going to be 0, 1, and minus 1. Right? And so we want to use the second derivative test, so now we should take the second derivative. Okay, so I'll slow down a bit. Okay, so we're taking the derivative of this guy up here. We get 15 times 4, which is 60, and then x cubed. And then we'll get 15 times 2, which is 30 times x, right? Okay, now we are just going to take our critical points and plug them into this formula we just found. So we're going to evaluate f double prime of minus 1, f double prime of 0, and f double prime of 1. So one thing to be careful for is make sure you're plugging your numbers, your critical numbers, into the right thing when you're using this test. So make sure you're plugging it into the second derivative, not the first derivative, and not the function itself. So keep everything straight. Okay, so this is just a matter of plugging in. So we would get 60 times negative 1 plus 30. So that'll give us negative 30, which is, of course, less than 0. Let's just go ahead and finish off the others. So we'll get 0 for both terms when we plug in 0. So that one's just equal to 0, which actually means the test fails. So maybe I'll write that down. So for 0, the test fails. For here we got something that is less than 0, and so that means that the function is concave up there. So this is a local, less than 0, concave down. Concave down, so this is a local max. Okay, and then when we plug in 1, we'll get 60 times 1 minus 30, so then we get 30, which is less than, not less than 0, it's greater than 0. Okay, and then that is going to be concave up, so we get a local min. Okay, so we were able to classify 2 of the critical numbers, but for the third one, the test did fail. So what we do when the test fails is we just go back to the first derivative test. So for x equals 0, we will use the first derivative test. Okay. So we can just create our number line, right? I'll put my critical points on here. And really, we just care about what's going on either side of 0. We really care about these 2 intervals on either side of 0. So we only need to take test points from those 2 intervals, right? So let's see, where's our derivative? So we got 15, so we have 2 terms. Try to keep everything in the frame. So we'll have our test points. So creating our sign chart now. we'll have a term for 15x squared and x squared minus 1. And then this is the sine of f prime. Okay, so like I said, we only need to take two test points, one from each interval that is on either side of 0. So I'm going to take -1/2 and 1/2. It turns out that 15x squared is always positive, so we get positive for both of those numbers. If we plug in -1/2 into here, we'll get a positive number. It will be 1/4, right? Yeah, 1/4 minus 1, so that will be a negative number. And then the same thing happens when we plug in 1/2. Since we're squaring it, we get the same answer out of this, so that's also negative, meaning that f prime is negative on the first interval and still negative on the second interval. So putting that on our number line, we see that the sign does not change. So this is f prime. So sine of f prime does not change at 0, so not a local max or min. Right? Okay, so what we get is that we have a local max at -1, a local min at +1, and that is all. That is all of the relative extrema. Okay. Now, this is the problem that was on a worksheet a little while ago. So I just wanted to go over it now. And so notice that here we're given the graph of the derivative. And so when we're thinking about how to analyze and answer questions about this, we have to be really careful. Like, we're dealing with the graph of the derivative, not the graph of the function. So, for instance, here we're asked, the first question is, on what intervals is f increasing? And so we have to think about what that means in terms of the derivative. When f is increasing, that means that, so we could rewrite this question to say, on what intervals, intervals, is f prime greater than 0? Because we know that f prime is greater than 0 if and only if f is increasing, right? So, looking at our graph now that we have that in our heads, where is f prime greater than 0? Well, it stays above the x-axis on -1 to 0. At 0, it's actually touching, so we don't count that point. So -1 to 0 is one interval where f prime is greater than 0, and then between 0 and 2, f prime is also greater than 0. Between 2 and 4, it drops below the x-axis, so it is not greater than 0. And then after 4, I guess we'll assume that the function stops right there, or you could just assume it keeps on going in this same direction. It's up to you how you want to interpret it. But we'll say it stops at 4.5. So these are the intervals on which f is increasing, because the derivative graph is above the x-axis on these intervals. And so we can similarly answer the question for what intervals is f decreasing, on what intervals is f decreasing, and that will just be the interval from 2 to 4 that we omitted in the previous part. So just to be complete, converting this into a statement about, or a question about the derivative, This is asking on what intervals is f prime less than 0. And so that will be from 2 to 4. Okay, now again, we're going to take this question. So it asks, at what points does f have a horizontal tangent? And think about what that means in terms of the derivative. When f has a horizontal tangent, that means that the slope of the tangent line is equal to 0. And that means that the derivative is equal to 0. So this is asking at which points is f prime equal to 0, right? And so when we look at the graph of the function, that's going to be everywhere that this graph touches the x-axis. So that happens here at 0, at 2, and at 4. So at each of those points, we know that f has a horizontal tangent, right? Okay, and then here it asks, at what value of x is f of x decreasing the fastest? So this is asking when is the derivative so this is a little awkward to state, but it's asking when is the derivative negative, so that means that the function is decreasing, and largest in absolute value. Or you could think of this as largest in magnitude. So that means that the value is negative, but the actual size, if we were to take the absolute value of that, would be largest. And so this is looking for the, like when we just focus our attention on the part of the graph where the derivative is less than 0, the largest magnitude is going to be the lowest point, which happens right there. It looks at like it's at 3.25. Right? So if we wanted to be more specific about what this means, at that point, you can see that if you trace this over to the y-axis, that looks like it will be -1. So that is going to be the steepest point of your graph of your function, and that will be when the slope is -1. And then after that, it will be still negative, but less steep, right? Because it will be a smaller slope. And then before that, it's also less steep. So the steepest point happens at that local minimum of the derivative, right? Okay, now this question is interesting. So it asks, which is larger, f of 0 or f of 2? And how do you know? So we don't know the values, and there's no way of figuring out what these values are. We only know the derivative, and so we can't actually assign values or compute them or anything from this graph. And so what we can do is just clean this up a bit. Okay, so we're looking at 0 and 2, and the information we do have is that, okay, starting at 0, we know that the derivative is equal to 0 at that point, and then it is greater than 0 on the interval 0 to 2. So f prime is greater than 0 on the interval 0 to 2. And what that means is that the function f is increasing on the interval 0 to 2. And so even though we don't know what value f started at 0, we do know that it was increasing all the way between 0 and 2. And so we can conclude that f of 2 is larger, right? Just because we know that f was increasing that whole time. So f of 2 is larger. Okay. So we'll talk about the next thing in the next video.